Okay, I think we're ready to start. We'll ask people in our audience who are on Zoom, because we have Zoom on in the room, if you will please not talk at all during the meeting, because whatever sounds you make in the audience can be picked up by the microphone. Um, so, so it helps if we can be as quiet as possible in the room. We do have people on social media who are with us tonight, and we have members who are also attending via Zoom tonight. So, so we're really happy to have all three groups here. I'm May Smith. I'm the TAAA president. Tucson Amateur Astronomy Association meets the first Friday of every month at 6:30. And if you're attending online, we usually have media active available for that meeting. And then we always post the meeting afterwards so that people can look it up online at any point in time and listen to our speakers. We have Terry Lappin, who is helping tonight with our media, and Jim Knoll, as well as Susan Knoll is operating the camera. So we've got a full house of volunteers doing a bunch of work tonight. We're really happy to be here and appreciate all of you coming. We have a really interesting, we, okay, we have a really interesting speaker tonight who is coming. And so Matthew, if you want to come up and kind of get started, we have Matthew Murphy, who is a PhD student who obviously is working very industriously on his research. And we're so pleased to have you here, Matthew. Because it may take us a minute to get the microphone for the speaker set up and make sure that it's working. Okay, the microphone does not yet appear to be activated. So we will solve this problem. Sometimes doing all the media that we're doing at one time gets a little confusing, and your probability of something going wrong is greater because we've got more microphones and things happening.
Hello? Thank
Great.
you for the
We've
live
got
commentary and solving these issues here. So we good to just go ahead and get started here? Awesome. Well, hi everyone. As was introduced, my name is Matthew Murphy. I'm a PhD student here at Stewart Observatory, working as hard as I can, hoping to graduate in the next few months. And so it's fun and exciting times. It's great to see you all. I didn't realize just how large the Amateur Astronomy Association and community was here in Tucson. So it's really cool to see everyone here in person, here in Zoom. Should be a fun and exciting night. So yeah, I was asked to come. Oh, I'm not even sharing my screen anymore. Uh-oh. Let me go ahead and get that solved. There we are. Turns out it takes one PhD to figure out how to get some slides going, but I haven't earned my PhD yet, so I don't know what that means. So anyways, I was asked to come here and talk to you about all the fun and exciting things that we're learning about exoplanets using the James Webb Space Telescope. And I could spend hours and hours going on and on about all of these different things, but I'm going to try to focus in on just a few cool and surprising things that we've learned. So I am going to talk about exoplanets, but I thought maybe I'd start this story just a little bit closer to home, and also maybe just take a quick step back to think kind of historically about how we got to where we are. Um, as I was preparing this talk, I thought a little bit about like how far back can we go to say when we first discovered like a planet, quote unquote. And I really couldn't find an answer because as far as I could tell, like humans have always known about planets in one way, for the simple fact that really there's a handful that we could just see with our own eyes. Um, I remember in the news a couple weeks or maybe months ago, there was this like planetary alignment going around the news. Did anybody like get some good photos? I'm sure you've all got some really good photos. I found this nice photo taken in the UK. We could see Mars, we could see Jupiter, we could see Venus. And I was trying to figure out like, humans have, as far as back as we can tell, we've seen these lights wandering around in the sky. We've known that there's these, what we call planets in the sky. And as far as I could tell, this really goes back to like basically the start of recorded history. The ancient Babylonians back 2000 BC were writing about the motions of Venus, trying to track Venus and figure out, how Venus's movements would say something about their grain harvest or their kings or whatever. So really, as far as humans have been walking around talking about things, we've been studying planets. But I don't think anyone really truly realized that these lights moving around in the sky were really worlds like our own until we took the telescope and actually pointed it at the night sky instead of just pointing it at distant pirate ships. So it was really Galileo in the early 1600s who had a nice telescope like this, probably quite small and modest compared to some of the telescopes you all are dragging around. But he pointed at the sky and we made some really, really amazing observations. I think arguably one of the most important observations that humans have ever made is this here. Sorry, I keep turning around. This here, which has, astonishingly become something that's probably really routine, even in amateur astronomy. Show of hands, does anyone know what we're looking at here? Right. Exactly right. We're looking at the Galilean moons here. When Galileo first, sorry, my laser pointer isn't even on here. First looked at the system, as far as I can tell, and I'm not a historian, so don't quote me on any of this, but as far as I can tell, this was really the first time ever that we realized that these lights moving around in the sky weren't just like weird stars doing weird things. We're like systems just like the Earth and the Moon, systems that could be planets just like our own. And this really turned, planets into worlds. I like to think of it that way. And this kicked off a pretty steady timeline of discovery going forward. As I mentioned, we have really since prehistory, all the planets that we could see with our own eyes. Galileo saw the moons of Jupiter and later Saturn in the 1600s. And then took a couple hundred years, or just over 100 years or so, until the first next planet was discovered, which is Uranus. This was the first planet that we couldn't see with our own eyes that was discovered in our solar system. Just under another 100 years later was Neptune. And then just under another 100 years was Pluto. And so roughly 100 years or so, roughly every 100 years, we discovered another planet out there in the universe. But this all changed just before the turn of the 21st century, when we sort of completed our census of the solar system and started looking beyond it. And in 1995 came the first detection of a planet outside of the solar system. This was 51 Pegasi b. And I'm not going to get too into the nitty gritty of what's going on here, because the details are irrelevant and not what I'm going to be talking about today. But this is sort of maybe unlike how we traditionally think about pointing a telescope at something and looking at it. But when we discovered 51 Pegasi b, we were looking at a star, and some clever researchers noticed that the star is moving a little bit further away from us over time. Then it slows down, starts moving toward us over time, slows down a little bit, starts moving away from us again. And it has this weird periodic motion going away from us, towards us, away from us again. That's actually due to this planet that's orbiting around it, tugging on the star periodically as it orbits. And they figured out that this planet is about a little bit larger than Jupiter, about half as massive, and it's orbiting a star in a period of about 4 days. And so its year is only 4 days long, which is kind of ridiculous to think about. And it really set a kind of weird but enticing precedent for what we might expect, what other kind of worlds could be out there. And so this became really the first time, well, if you count Pluto as a planet, this became the first time ever that we actually discovered 2 planets in the same century. If you don't subscribe to Pluto anymore, we're still no problem. But since then, we've found thousands and thousands of more planets outside of the solar system. Can I get a show of hands? Does anyone actually know how many exoplanets we know about today? About 5,000. That's pretty close. I think last I checked, it's like 5,800 something. There's a little gray area of what you count as like detected and confirmed and such. But the point I want to make is that the discovery rate has just exploded in recent years. We went from 1 here in 1995 to 30 years later, we're up, forgetting the exact number because it's just so ridiculously high. And as we'll talk about later, all of these discoveries have revealed, some things that make sense, but a whole lot more things that just don't make sense. And there's a lot of mysteries, a lot of weird planets, and a lot of just exciting puzzles that we're just starting to figure out how to try to solve. So I'll share a couple exciting things today, but really this is in no way a solved problem. In no way are we anywhere close to figuring out all the weird things that are going on. So for some context, I showed you 51 Peg. That curve you were seeing was something called a radial velocity curve. But the majority of the planets that have been discovered, and the majority of this sort of discovery curve you saw on the last slide, has been through the transit method. And if you've ever seen a solar eclipse, maybe I'm sure most of you might have even seen like transits of Venus across the sun or transits of Mercury across the sun. You're probably well familiar with how this works. I found this really cool video on YouTube of Venus transiting the sun. I think it should come into frame soon. There's our little friend Venus here. So when we're trying to discover exoplanets, and this transect technique that has been really, really successful in detecting exoplanets is doing exactly this for thousands, tens of thousands of stars in the night sky. And it seems like deceptively simple. All we do is we stare at a star, we wait a while for a planet to go in front of it. When a planet does go in front of it, it blocks out some light. We see the star's brightness dip over time, and that tells us the planet's there. You have a quick question here? I think that's just a camera thing. I don't know exactly where this video comes from. I'm not sure. Venus is assuredly not just doing weird bounces in its orbit. I think that's just that's probably it, yeah. Of course. We just had a quick question. Why is Venus kind of seeming to move up and down across the face of the sun? Probably just due to what the satellite that's taking this video is doing. And so what's amazing, I think, about this technique is that it's really, really powerful. It's allowed us to find thousands of worlds outside of the solar system, but it's something that you could do just with your 14-inch telescope in your backyard, pointed at a star, and you could see this exact effect. And using this transit technique, we've assembled a massive population of planets. And the spot here is what we currently understand about the exoplanet population and its diversity. Here I'm plotting planet mass on the y-axis and the planet's radius on the x-axis. Both of these are in log scales, basically powers of 10, and both axes are plotted relative to Earth. So it's mass in terms of Earth masses, radius in terms of Earth radii. Here's Earth, and I plotted all of our solar system planets just for reference. And each black dot here is a confirmed, not necessarily studied, but confirmed and detected exoplanet. And what I think is interesting, at least one thing, is that these planets seem to fill out a nice sort of continuous curve here. We have planets that are like Earth and Venus, all this nice curve up to planets that are just like Venus. Keep going, planets that are just like Jupiter, planets that are just like Saturn. And so we have planets similar to those in our solar system, but as I kind of mentioned, there's a lot of things in between. And for me, these in-betweeners, planets here, they're kind of between Earth and Neptune, planets that are between Neptune and Jupiter, these are the weird things. What the heck is going on here? What does it mean to be an in-between planet? And these are what I'm going to focus on in this talk here. So in particular, I'm going to focus on two regions of this parameter space. First, what is going on here? These are planets that are somewhere in between Earth and Neptune. What does that mean? Are they like Earth, but you just made Earth bigger? Are they like Neptune, but you just made Neptune smaller? Is it somewhere in between? What's going on? And second, I'm going to focus later in this talk on these planets out here. These are things that are like sort of Neptune mass, but maybe Jupiter sized. What the heck does that mean? How the heck does that work? So first, I'm going to focus on these between Earth, between Neptune planets. Like I said, are they like Earth, but just bigger? You could call that a super Earth. Are they just like Neptune, but smaller? You could call that a mini Neptune, or is it some combination of the two? So to give you kind of a quick, unfortunate spoiler, we don't really still know what's going on with these planets. And so I could convince you one thing or another, but to tell you the truth, we have no idea. One thing we do know is that these planets seem to be weirdly very common. There is a bit of a division. So what we're seeing here is the number of planets per star as a function of how big that planet is. So for example, here's Earth, one Earth radius. There's about 0.05 Earth-like planets, Earth-sized planets per star. So if you had 50 stars, maybe you'd find one Earth around it. Here's Neptune. There's maybe 0.01 Neptunes per star. So if you had 100 stars, you might find one Neptune. But these in-betweeners, these super Earths, these sub-Neptunes, I'm happy to answer any questions about what this division is, but I'm not going to go into it. They seem to be super, super common to the point where these sub-Neptunes, you might have one for every 10 stars. So if these are the most common type of planet, which it seems based on the statistics they might be, we don't have one in our solar system, so we have no idea what these might look like. And so there's a huge open question and understanding of what planets might be like. And there's been a few leading theories proposed over the last few years. One is that maybe they really are just kind of miniature Neptunes. You took Neptune, you just shrunk it down a little bit. A more exciting theory, in my opinion, is that these are actually water worlds, kind of large, really water-rich, maybe ocean-bearing worlds, something like that ocean planet from the movie Interstellar. So to try and solve this puzzle, myself and a team of astronomers, both here at U of A, really around the world, have been looking at one sub-Neptune in particular, our good friend GJ1214b. It's a planet that's about 2.7 times the size of Earth. So it's kind of right in the middle of this distribution of really, really common planets. It's about 8 times as massive as Earth. And by Earth standards, it's pretty hot. There's a temperature of around 560 degrees Fahrenheit. It's a little bit hotter than a summer day here in Tucson, but it's a bit toasty. And it orbits an M star that's about 47 light years away. And this planet has, as I'll show you in a couple of slides, has been the topic of study with the James Webb Space Telescope, with Hubble, to really, really capture the interest of the community. And so I'd actually, before I get started, I'd love to take a quick vote. Show of hands, does anyone think it's a mini Neptune? We'll just go just one. Anyone think it's a water world? Maybe a trick question, does anyone think it's neither of the above? We got some hands here. So one of the reasons we picked this planet in particular is because it should be the easiest of these planets to study. This is a plot of something that we call the transmission spectroscopy metric, or TSM, which is basically a fancy number that we use to calculate how easy a planet, based on its mass, its radius, its temperature, should be to characterize and learn about its atmosphere. And based on the TSM, GJ1214b, you notice how it's higher than basically all of these other points. Should be super, super easy to study, figure out what's in its atmosphere, solve this problem, call it a day, go home. You might have heard about WASP-39b in the news. This was the first exoplanet that JWST was pointed at. It's even supposedly easier to study than WASP-39b. And as you can maybe guess, but by me saying should be, you might be able to guess this wasn't quite the case. And to kind of give you a sense of why, let me show you and kind of walk you through exactly what we're measuring, how exactly we're studying these exoplanets. So what we're looking at here is something called a transmission spectrum. Remember, we're looking at planets transiting their star. These planets have atmospheres. Atmospheres have molecules in them. And molecules and clouds and things will absorb and scatter light in different ways. And if we look at the transit at different wavelengths, those molecules sometimes will absorb a lot more light at different wavelengths. And so we look at the transmission spectrum, we'll see this really big bump. And these big bumps tell us that there's some kind of molecule in the planet's atmosphere. So when we see bumps, we're happy. When we don't see bumps, we're not happy. So this is not GJ1214b. This is kind of an example planet of an example of what a transmission spectrum should look like. So we're trying to study JJ1214b. Should be the easiest to study. We should see something even bigger than what we see here. And this data in particular, this is from the Hubble Space Telescope. And when we pointed Hubble at GJ1214b, what we saw here is this sad little flat line. Now you notice there's no big bumps here. We're not happy. What's going on? And so this was unexpected, and for nearly a decade, this planet remained a mystery until we launched the James Webb Space Telescope. And maybe JWST can do better. Over here on the right now is another transmission spectrum of the same example planet measured with an instrument called MIRI. That's the mid-infrared, I forget the acronym, but it's one of JWST's most powerful instruments. And you can see for this example planet, it's an even larger bump here, even larger features. So, okay, maybe we point MIRI, GJ1214b, maybe we'll find something. But once again, we find a sad, flat, little transmission spectrum. And once again, this planet just refused to give us its secrets. So what the heck do we do? What the heck is going on with this planet? But, maybe third time's the charm. See, there's a lot of empty space here in between these two spectra, a lot of wavelengths we could still tackle, try to figure out what's going on. JWST has this other instrument called NIRSPEC that operates in these intermediate wavelengths. It's a very precise, very high resolution instrument. When we pointed NIRSPEC, or when people pointed NIRSPEC at this other example planet, once again, we saw these really booming features, really strong molecular absorption. So, okay, this is our chance. We're going to figure it out. And so my team and I, we pointed near spec GJ1214b, measure its transmission spectrum. Surely this will be our chance. And this is what we found. Once again, at least at first glance, seems like another sad flat line. I heard someone say there's something there. And if you have a keen eye, you might notice, and maybe you squint a little bit and trust me, there's a teeny tiny little bump here. But small bumps can change everything sometimes. So looking just at the JG1214b observations, all these gray points are the blue data you just saw. And all of these other lines are our best fit models. So this black line here is our best fit model to the planet's overall transmission spectrum. And as we've seen, you'll notice it's kind of basically all flat. There's some teeny tiny little bumps here. We'll get to those, but for all intents and purposes, it's all flat. Currently, the only way we can explain why it's so flat is if there's some kind of really thick, strong haze in the planet's atmosphere. Like some kind of pollution gone horribly wrong, some really thick smog in the atmosphere. If we didn't have that haze in the atmosphere, all of these strong sort of lower bumps, this is molecular absorption that we would see if it weren't for the haze. But we see this big flat line. And if you're keen, you'll notice in this region here, there's a little bit of region. And sorry, I forgot to mention, all of these different colors are different molecules. So the blue, I think, is water here. There's a bunch of water bumps. The orangish is CO2. And there's one region here where the CO2 absorption peaks above this cloud layer. And that's responsible for this teeny tiny little bump here that we saw using near spec. Near spec, just for reference, is these NRS1, NRS2 things. This is an astonishingly small signal. It's about 10 parts per million in amplitude. I looked it up yesterday. There's like just over 1 million people in the Tucson metro area. Observing this bump is equivalent to just taking 10 random people out of the entirety of the Tucson metro area, giving them like a silly hat, letting them loose, and I just told you to go out and find those 10 particular people. So it's a really small signal, but using the precision of JWST, we were able to pick up this teeny tiny little bump, telling us that there's actually carbon dioxide in this planet's atmosphere, peaking above what's otherwise this really thick, really obscured haze layer. So we have a planet with a lot of haze and what has to be a lot of carbon dioxide. So thinking back to where we started, and remember we took our vote, hopefully you remembered your answers, what does that actually mean for what this planet is? Is it a mini Neptune? Is it a water world? If it was a mini Neptune, what we'd expect is we had an atmosphere that was sort of pretty big, with lots of hydrogen and helium in it. If it was a water world, as I mentioned, there's a lot of water in the atmosphere. We'd see, a pretty thick atmosphere, a lot of steam, a lot of things. But instead, what we found is a lot of haze, a lot of carbon dioxide. So really, as I said, it was a little bit of a trick question earlier. It's neither of these things. So I'm sorry to have led you on a little bit. But really, and take this with a little bit of a grain of salt, it seems like GJ1214b it's maybe some kind of like super Venus. It's this thing that doesn't really make any sense. But it's a big planet that's like just a little bit smaller than Neptune. And just like Venus, it seems to have this atmosphere that's just full of carbon dioxide and shrouded in this really thick, mysterious haze layer. Now, I'm not saying it has a surface like Venus. It probably doesn't. It's probably totally different. But at least our atmosphere seems somewhat similar. And something kind of disheartening in ways and exciting in other ways is that this is almost certainly not true for all of these sub-Neptune exoplanets. And there's probably a whole diversity of these things that we're just starting to explore, just starting to uncover. So maybe GJ1214 is just this weird outlier. Maybe this is actually telling us something about maybe this sort of strange, weird, cloudy planet is actually really, really common in the galaxy. Who knows? So I thought here maybe I'd take a quick break for questions. If anyone has any questions before we get into the rest of the talk. Yeah. So sorry, we beat the mic runner. But the question was, is this planet really close to its star? Maybe the heat or the sunlight is sort of driving whatever's going on. Yes and no. As I mentioned, its temperature is at about 600 degrees. It's certainly closer to its sun than Venus or even Mercury is to our sun. And so that does play a role. But we've found much hotter planets, much closer in planets that are not at all cloudy like this, that are not at all like so full of carbon dioxide, so full of clouds. And so there seems to be something we're missing. Maybe the stars really like have a lot of UV flux that's going in and driving some kind of out of control haze and smog formation. Maybe that's the answer. But it's a little bit more of a complicated puzzle. Yeah. Any other questions? We have one.
Wait. Do we know how these planets are formed to begin with, how they originated?
That's another excellent question that I can't personally answer. We think we sort of have an idea of how these planets are forming. We think that, these systems are born as big, like pebble fields, a bunch of little rocks that assemble together, become gravitationally bound, and then start to accrete atmospheres. But obviously, it seems weird to do that like right next to a star. These planets are all really, really close to their stars compared to Earth, compared to Jupiter. And we don't think that they actually formed there. We think they formed somewhere further out from their star, picked up some hydrogen, helium, heavier elements, and then there was some kind of like dynamical process, some kind of gravitational process that took those planets and like sent them careening on in closer to their stars. And so where they are today is not necessarily where they formed, but we think they formed by like accreting rocks and then starting to accrete gas into the atmosphere. We have another one over here.
Given the compact nature of many molecular clouds where stars form, what is the likelihood that many of the exoplanets that we're seeing are not actually native to their host star, but were exosolar captures from another star within the molecular cloud?
That's a very interesting question. I think not too many. These environments that stars are forming in, they are dense compared to like the overall size scale, but the stars themselves never really get too close to each other, and I think the planets themselves are forming close enough to their host stars that the host stars, they're like mother stars, I'll say, are able to keep a nice tight hold on them. And you certainly can have cases where some planets, through some interactions, are like thrown out of their host star system, and that certainly does happen a lot. But especially for these really close-in planets, I think it's very unlikely that these are like orphan planets. Yeah. So maybe we'll go ahead. Yeah. And run you mine.
Yeah, so the chart that you showed this was the planet to look at. Can you explain why that one stood out so well?
So the question was about this transmission spectroscopy metric I was telling you about. So what this is effectively is kind of a guesstimate of what the sizes of these features we see in the transmission spectrum should be. And it's some combination of like, if you have a planet that's really massive and has a lot of gravity, then its atmosphere is kind of kind of be squished. But if you make that atmosphere hotter, hot gases expand. That makes the atmosphere a little less squished. And sort of how squished the atmosphere is tells you how big these features are going to be. And so it's a combination of like mass, radius, gravity, temperature, what we expect the composition to be, sort of guessing of like how big these features are going to be.
So are you specifically looking for certain molecules in the atmosphere? Or is this really not connected to individual molecules?
It's a general guesstimate. It's based on something we call like the scale height, which is like how sort of a measure of how puffy or big the atmosphere is, and the composition plays into that a little bit. But generally, for any composition, if you have a more puffy atmosphere, your absorption signals will be bigger, and you'll get a higher metric.
Okay, we have a few questions on Zoom. Let's see, wait a minute. It's interesting. I have questions from our last meeting. How'd they get there?
I can try my best. No promises.
We will get to the Zoom questions at the second part.
Sounds good. Sounds good. So we should probably get ahead and get started with this second part, shall we? Right. So we're back looking at this weird, large population of exoplanets. I hopefully maybe convinced you that there's a lot of weird, funky things going on in this intermediate regime. Let's move to talking about what's going on out here. What's up with these planets that seem to sort of lie away from where most of the planets seem to be and have this weird combination of mass and radius. These planets out here, like I mentioned earlier, they seem to be sort of about the same radius as Jupiter, but roughly the same mass as Neptune. What does that mean? To kind of put that into like maybe somewhat more familiar terms, show of hands, anyone here like golfing? Any avid golfers out here? Nice. I'm a Callaway man myself, I will admit. So to kind of give you a sense of what these planets are like, I want you to imagine you took a golf ball, right? Something the mass of a golf ball, but you made it sort of puffed it up to be as big as a volleyball. That mass radius combination took me a while to figure this out. It's actually about the same density you get for these weird planets. And it doesn't really make much sense to me how you could get a planet like this. And sort of the poster child for these weird density planets is the planet WASP 107b. And this is a bit of a spoiler here, but we came to call it the popcorn planet. Why do we call it the popcorn planet? WASP 107b has about Neptune mass, it's about Jupiter radius, and its temperature is a little bit hotter than GJ1214b was. It's about 750 Kelvin, or about just under 900 Fahrenheit. And its density, about 0.1 grams per centimeter squared. So we called it the popcorn planet because it's even less dense than popcorn. Popcorn's density is about 5-6 times the density of this planet. I took this one further. In fact, this density is exactly the density of a golf ball that's the size of a volleyball. Did some hard work in preparing for this presentation, but alas, it's the popcorn planet. So that raises the question of how do you make a planet like this? And even once you made it, what the heck does it look like? What I've kind of hidden from you this whole time is that this black example planet spectrum we were looking at earlier, this is WASP 107b. It has really, really, really whopping, huge absorption features all across its transmission spectrum. Which, sorry GJ1214b, WASP 107b, super easy to study. So what's going on in its atmosphere? But with all this data and all this really beautiful transmission spectra, we were able to get a really, really good insight of what's going on in its atmosphere. And from there, start to uncover, what's making this planet look the way it looks. And so this is all the transmission spectra data here plotted in a much nicer set of axes than I had earlier. And all of these colors here are the contributions from different molecules in the atmosphere. So we found water, that's this light blue here. We found a lot of CO2, that's this pink. We found CO, that's this, purple over here. Found some methane, that's this green here. This is a really weirdly flavored piece of popcorn. Found a whole lot of molecules in its atmosphere. But what I want to draw your attention to is this methane. Why does methane matter? There's no cows in the planet. Let me assuage any misconceptions here. But this methane matters. Why does this methane matter? Methane matters because we can use it kind of like a thermometer for exoplanets' atmospheres. Carbon chemistry does some things I don't fully understand. I'm no chemist. But carbon chemistry kind of works out to be that when you have a hotter gas, that gas should have less methane in it because that methane gets converted to other things like CO, CO2. But if you cool that gas down, all of those convert back into methane. So if you have a cooler planet, it should have more methane. If you have a hotter planet, it should have less methane. So we can kind of use the methane abundance that we see in the atmosphere as a little bit of a thermometer for how hot that planet is, or the inverse. But we know, based on its period, based on how far away it is from its star, we know how much methane WASP 107b should have. It's a certain temperature, it should have a certain amount of methane. And in this plot here on the right, this is a plot of basically just methane abundance in log scale on the x-axis here. This black line is how much methane it should have based on its temperature. But what we measured is this gray distribution here. We measured 10,000 times less methane than this planet should have based on its temperature. So how does this happen? What we think is happening is that there are tides that are tugging on the planet, puffing up its atmosphere. This is my lovely drawing of the WASP 107b system. Here we have WASP 107b orbiting its star up here. And, it's orbiting a star. It's receiving a lot of sunlight, and that sunlight is heating up the upper atmosphere. And based on the temperature, we infer from how much sunlight we know is hitting the atmosphere, it should have some amount of methane. It should have a fairly hot atmosphere. Sorry. Should be a certain temperature, should have more methane than we see. And so in other words, the lower atmosphere is hotter than it should be. So what we think is happening is that the star is kind of tugging on the planet. There's no rope, but imagine this rope is gravity here. There's tidal interactions that are interplaying between WASP 107b and its host star, similar to the way that the Earth and the Moon have tides that tug on each other, similar to the way that Io and Jupiter have tides that tug on each other, and actually, in the case of Io, lead to a lot of volcanoes and volcanic activity. There seems to be some tidal interactions between WASP 107b and its star that are heating up the interior of the planet, making it hotter than it should be, lowering the amount of methane, and in the end, puffing up the planet. And so it's getting heated up in the interior. That heat has to, heat something up, so it heats up the atmosphere, puffs it up quite a bit. And so this planet that's really, really weirdly low density, it seems to be, as far as we could tell, something like if you took Neptune and you puffed it up, as opposed to sort of the inverse of taking a Jupiter and like making it weirdly light. And so that's why it's popcorn. But in my last few minutes, happy to tell you about how we're taking this even further and trying to uncover even more about what's going on in this weird Waspinus 7b atmosphere. And this is what I personally work on, which is trying to use JWST to better map out the atmospheres of exoplanets. We've sort of previously just been looking at like spectra of how much light the atmosphere blocks as a function of wavelength, but atmospheres are 3D. Atmospheres have, spatial dimensions. Here in Tucson, it's one temperature. Out in Antarctica, it's another temperature. How can we sort of translate that into our observations of exoplanets? As I mentioned, we're looking at these things in transit. And when we do, we're actually looking through two distinct regions of the atmosphere. So we're kind of looking top down at the system. Here's us in JWST looking at this planet. We're looking at one hemisphere through here, looking through another hemisphere over here. Obviously, none of this is to scale. But these planets, they're really close to their stars, receiving a lot of sunlight. And so, one half we expect to be really, really hot. The other half we expect to be really, really cold. And not only that, these planets are rotating as they go. So some of that hot gas is kind of pushed one way, some of the cold gas is pushed the other way. And so we might expect one side to be, a lot hotter than the other side. Just for some reference here, we have the planet's day side up here, we have the planet's night side over here, and we kind of call this half here the east hemisphere, or the east terminator. The other half we call the west half, the west hemisphere, the west terminator. Just to give you some reference here. And sort of these are the regions exactly that we're seeing when we look at it in transit. And so we should be able to see, oh, hey, this half is a little bit hotter. Oh, hey, this half is a little bit colder. And maybe that'll help us like sort of try to uncover these weird things and start to try to explain these mysteries going on with these planets. And to kind of spoil things again a little bit, as I'll show you, we need to update this popcorn planet title, because WASPO 7b is actually a bit of a lopsided piece of popcorn. And I'll show you why. So using JWST, I've been working on developing ways to try to, in transit, tell the difference between one side of the planet versus the other. And it really wasn't until JWST that we had the precise data to be able to do this. And so over the past year or so, I've been working really, really hard on all of the observations of WASP FMB to figure out exactly what's going on the east, what's going on the west. What we found is that, indeed, one side of WASP FMB is actually really significantly hotter than the other half. Its east hemisphere is at a temperature of about just under 1,000 Kelvin, but its west hemisphere is almost 300 degrees Fahrenheit colder. It's a really, really extreme difference. On Earth, day to night, summer to winter might be, 60 degrees difference or so. This is a 300-degree difference. And because hot gases expand, the east half, the east hemisphere, is actually physically larger than the west half by order thousands of kilometers. Not only that, the east half seems nice and clear versus the west half seems to be really cloudy, probably because it's colder. And there also seems to be some asymmetry in the amount of molecules on each hemisphere. Whereas this colder hemisphere seems to have more CO2, also this other molecule called SO2, which is sort of a photochemical product. And so it's this really, it's not a nice, perfectly spherical, lovely piece of popcorn. It's something a little bit lopsided. And so it's this really weird planet. And it's just sort of setting the stage of all of these weird but exciting and amazing discoveries we can start to make and start to uncover the diversity of planets out there in the solar system, out there in the galaxy. So that's all I have. Leave my summary here, maybe take the rest of your questions. Thank you very much.
Okay, let's start on Zoom for the first half questions that I didn't give earlier. Matthew Oda asks, is the spectroscopic detection of O2 in exoplanet atmospheres by the JWST a surefire indication of life?
Absolutely not. Yeah, it's kind of a really rich industry going on right now of how can we, if we, we want to detect, we want to find life at the end of the day. So how do we do that? And one of the ways we go about doing that is finding some kind of gas that only life produces. And so if we find this gas in an atmosphere, we know life is there. And there just doesn't seem to be any good winner there. Things like methane that are produced from, cow farts, other kinds of molecules that are produced by, algae. Basically anything we can think of has some counterpart that can be produced very finely without life. And so there's really no good answer there of like, how can we definitively find life? And if we find a molecule that we think life produces, how can we prove it? And so if you see some claim of a biosignature, that's what we call these gases, we call them biosignatures. If you see some claim of a detection and a claim of aliens in the news, I advise you don't believe it, unfortunately.
All right, and one more question from the first part. Phil Yelly asks, how do you separate the spectrum of the star from the spectra of the planet?
That is an excellent question. Let me see. So I'll start maybe here. This is sort of first order what we're actually measuring here. This is the light curve of a transit. And so before the planet transits its star, we stare at the star for hours upon hours. And so we have a good handle of like what the star itself looks like. And then once the planet enters transit, we know what that system is of the star minus the planet. And so basically just subtracting the two, we know really well what the star is doing on its own. And so we can subtract that out really well. And what that leaves us then is just the planet's signal. Yeah, hopefully that answers your question.
All right, questions in the room? Hang on a second. Got two down here.
I'm just curious. It seems like you would have these transits are close to the sun. Those are the ones that you're picking up more often. So isn't that introducing a sort of a bias in terms of the demography of these exoplanets?
It absolutely is. Yeah, you're absolutely right. Oh, geez. Okay. I don't know if I'm committed now to flipping back to that slide. Yeah. This plot here is just like a subsample of about 1,400 transiting planets that also have measured masses. Like, this is in no way representative of the actual intrinsic planet population. And yeah, we're absolutely subject to these detection biases and all sorts of things. And sort of a very open area of research right now is like, how do we account for these biases to take what we do know and take what we, are biased to see, and from that figure out what's actually out there. But yeah, sorry. There are pretty good estimates. And in fact, it's sort of these estimates that tell us that like these between Earth and between Neptune planets are some of the most common in the galaxy. There seem to be even more out there than we actually see transiting. And actually probably a lot more Earth-sized planets too. But yeah.
Yeah, in that plot you have up there, the below that main sequence, if you could call it that, are the planets you've been telling us about that are very low density, and they have to be puffed up gas. What else could they be? There's also a lot of planets way high above it, and those can only be, well, maybe instrumental errors or very high density, much higher density than terrestrial matter. What's going on with those?
So those, right, those sort of could be like the weird other counterpart of those. Um, it's sort of a bit of also a misrepresentation here. A lot of these probably aren't real. If you look really closely, you notice some of these have like little arrows on them. Those are just kind of upper limits. Sometimes it can be hard to measure the properties of a planet, hard to measure the radius. And basically, these are kind of like upper limits. The planet's radius has to be, it can't be more, or sorry, not the radius, the mass. It's really, really hard to measure the mass. And
Fine.
so,
But you do have one point up there, just at the tip top there. And you also have a lot of Jovian mass planets that aren't limits, that look like they maybe have 10 times Earth density, and they can't be rocky, can they? So what's going on with the ones that are high up in the Jovian? And what's that one Neptunian that's made of neutronium or whatever?
so I have to be honest, I have no idea what's going on with this guy. Yeah, that's weird. I'll have to look into that. I don't know what's going on there. Sometimes you can get like, so I pull these all from a big archive. Sometimes you can get weird numbers, but I'm not sure what's going on with that guy. As far as the Jovians go, there's actually something interesting. Like there's sort of what we call a turnover in the mass radius curve, where like once you get up to kind of Jupiter's size, sort of nominally, like you'd expect if you take a planet, you pile on more and more gas, you would expect that planet to get bigger. But you reach a certain point where, as you start to pile on more gas, like the density of the gas gets really high, the self-gravity of the gas starts to get really strong. And so if you actually add more gas, it starts to actually shrink the planet a little bit because there's so much mass in the planet that it has such high gravity that it pulls and contracts that gas in a little bit more. And that sort of turnover happens sort of roughly a little bit bigger than Jupiter. And so in this regime, basically, they're all very Jupiter-like compositions, structures, but you reach a point where, like, as you add more mass, you can't really make the radius any bigger until you add like so much mass it becomes a star. And so that's what's going on here. Basically, you reach this turnover point where the planet just has such high gravity that just by adding more gas, you can't make it any bigger.
Can you go to the slide that has the orbital diagram between WASP and its host star real quick? It'll make more sense.
This guy?
The one where the day-night side. Keep next one. Yes. So obviously WASP has its own day-night cycle, and it doesn't seem like it's tidally locked, at least from how it's presented here. What is the contribution to its orbital period, its own rotation, to the offset between its day and night side temperatures?
Great question. Sort of to nip it in the butt there, it is tidally locked. This planet is on a roughly 5-day orbital period. And at that point, you get so close to your star that just like the moon gets locked to Earth, your planet gets tidally locked to its star. It's kind of an interesting separate question there of what does that mean for a planet with an atmosphere? Like, is the gas just kind of locked into one place? Not quite. What that kind of means is that like the interior bulk of the planet is locked tidally to its star, but the atmosphere is allowed to like super rotate on top of that. And that's exactly why we're able to see that gas that's sort of on the permanent day side of the planet getting really, really heated up by that permanent sunlight that's starting to circulate around the planet. And that's what's blowing through the one half. Gets to the night side, it cools down, and it starts to blow through the other half. And that's why we're able to see the asymmetry that we see.
Other questions in the room?
You mentioned that it's challenging to measure the mass of these exoplanets. How do you guys actually measure those?
Great question. I'm going to try to quickly flip back all the way back to the start. So there's two main methods. One method is exactly the method that we use to actually detect the first exoplanet. Because these planets are so close to their stars, they're gravitationally interacting with the stars, and as they go around in the orbit, they tug on the star, and they make the star appear to go sort of away from us, towards us, back and forth in this motion. And we can measure this. Looking at the spectrum of the star, we can tell how fast it moves away from us, how fast it moves towards us, and that speed is directly related to the mass of the planet that's tugging on it. And so basically, when we look at these radial velocity curves, we call them, how high the amplitude of these curves are tells us how massive the planet is. There's another method we can use called transit timing variations. Sometimes because of funky stars, we can't actually measure this very well. Another method we could use is like if you have a system with a lot of planets in them, the planets will actually tug on each other as well. And that can sometimes make the transits that we go to look for sometimes happen earlier, sometimes happen later as the planets tug on each other. And looking at those timing variations, we can also start to infer what the mass of the planets might be. So that's another method, but that's a little bit harder, a little bit less precise. But it's primarily this looking at the velocity of the star as the planet tugs it that we use to get its mass.
All right, if there's no more questions in the room, so we have on Zoom. Let's see, Matthew Oda asks, have you studied data from the recently concluded Kepler Space Telescope mission in your studies?
Yes and no. Personally, I haven't used any Kepler data, but Kepler has, been one of the most foundational missions that astronomy has ever done. And in fact, the plot I've shown of all the planets, mass and radius, a lot of those come from Kepler. And so without Kepler, we wouldn't know about most of these planets. And while I don't use the data, I use the fact that Kepler found the planet in the first place to go and look at it with other telescopes.
All right. Laurel asks, when you are eventually able to eliminate the specific solar interference, would your example planets maybe become more clearly water world-like or Jovian-like?
I'm not exactly sure what you mean by solar interference, but there definitely are. It's actually a really big problem, especially for studies of terrestrial, maybe Earth-like exoplanets, where, right, in an earlier question, I was talking about how we can just subtract the star's signal out and get the planet signal. Obviously, nothing ever works perfectly, and in a lot of cases, we don't fully know what the star is doing. And in many ways, if you have especially like sunspots, star spots on the star, those can sort of add their own features and slopes into the transmission spectrum that we measure. And that is often a problem. In many cases, we know how that works, we can solve it. But in a lot of other cases, we don't really have a good understanding of what certain stars are doing and how those affect the spectrum that we think the planet should have. And so it's a bit of an open, big problem here. But hopefully in the next few years, we'll figure out exactly how to solve that and hopefully then be able to start studying, even Earth-like exoplanets.
All right, and let's see, Matthew also asked, does the JWST have an occulting mass that can block out starlight so the spectra of exoplanets can be seen easier? And Alex Pacheco said, yes, there is one on NIR NIRCam.
That's right, yep. I wish I had a picture of it. Yeah, it's not personally what I do. I mostly look at transiting exoplanets, but there's a whole really amazing field of science looking at doing exactly this. Where you kind of put a fancy thumb over top of the star. That's the coronagraph that JWST has. And if you do that really well, you can block out the star's light and directly see the light of the planet. And people have done that. People have made some really amazing discoveries doing that. From a Google, you could find some really cool images. Wish I had something to share, but I don't, unfortunately.
All right, and lastly on Zoom, Matthew just says FYI 51 Pegasi B is officially named Dimidium.
Interesting. I did not know that.
Did not either. All right, anything else in the room? Wait, do we have one up there?
We want to go there. Of
Okay.
course.
To get you on the microphone.
We want to make sure those on Zoom can hear you. Thank you.
They seem to be pretty abundant as far as how many, you're finding a bunch of planets, but have they found any stars that you can say, yes, this star has absolutely no planets around it? And would that be a curiosity in and of itself?
That's a great question. I think no. There are definitely a lot of stars that we have not found a planet around. But to say then that that definitively means it has no planets at all is kind of a really hard gamble to make, especially because, like we were talking about earlier, there's a lot of biases we have right now, and like we can only find the easiest to find planets. And so planets like Jupiter, planets like Neptune that are kind of further out from their star are a lot harder to find. And so there are probably tons of these that we just haven't found. And the statistics we have right now tell us that probably every star has at least one planet around it. And so planets are really, really, really common.
Any other questions? Okay, I don't see any others.
Thank you all.
Oh, thank you, Matthew. Now, can I inquire when you graduate?
May 16th.
May 16th.
May 16th.
Wow.
Yeah.
Congratulations.
Thank you. Thank you. Yeah. And working hard on the thesis, trying to get that finished.
Now, are you staying in Tucson after you graduate, or are you going to leave us?
I'll be heading to Michigan.
Michigan.
Yep.
Okay.
I got a postdoc job at Michigan State, starting there in August, and so I hear some boos. That's not good. Go Spartans.
So then are you going to be continuing to do some research and when you're in Michigan, or are you going to be all involved in teaching and not have time or something?
No, I'll be purely doing research. And in fact, I'm hired to work on a JWST program that is going to be looking at more of these sub-Neptune exoplanets, trying to figure out exactly how they form, what they're like exactly like right after they're born. So I'll be doing a lot more JWST research. Yeah, real deep into that. Yep.
Well, super, super. Well, once you come and speak for us, then you're obligated to come back in the future when you have some other data that you can report, and you can do your presentation from Michigan on Zoom. And so just let us know when you have some other interesting things to share with us.
Would be happy to.
Okay.
Always happy to.
Thank you so much.
Yeah, thank you.
Okay, so next on our agenda, we have Dr. Eric Krakashka, who is going to give the planet report for the month. And Dr. Krakashka works in the Lunar and Planetary Lab at the U of A. So thank you, Eric.
Okay, with the planets, there are not too many planets in the evening sky. Only Jupiter and Mars are still visible there. Jupiter is setting around 11 p.m. or so. It's close to Aldebaran, as it has been a few months. And then a little further up, high in the sky, is Mars. It's transiting around 7 p.m., so just when it gets dark, at 80 degrees high. But it's not as big anymore as it was, because it's almost twice as far as it was just a few months ago. Still arc seconds, 8 arc seconds in diameter. And that means in a telescope, you just can see a few details. It's near Pollux, and it will move away from Pollux quite soon. And then there's no planet around midnight and early morning, but around 4 a.m., the bright Venus rises in the east. And in the second half of the month, it reaches the maximum brightness, minus 4.8. So it's really just like a really bright light source that you see in the east just when daylight, well, twilight is coming. And if you have a telescope, it is very beautiful right now because it is a very slim crescent and large diameter, but within the month it will get thicker and also smaller because Venus is moving away from us. And then closer to sunrise, Mercury and Saturn are rising. Right now, not yet visible, but around the 10th of April, they'll be far enough from the sun in angular separation so they can see them at least looking with binoculars. They're extremely easy to find because you just look 6 degrees below Venus. Venus, of course, is very obvious. And there you find those two. Mercury is to the left of Saturn, that's how you can distinguish them, and it's also a little brighter. And what's interesting with those two planets, they stay really close to each other for several weeks. They were already close, and until the mid-month or so, they stay 2 degrees from each other, and then Mercury finally tries to speed up and get away from Saturn. But there's actually no conjunction in right ascension. It means usually when two planets path each other, then when the distance is closest, that's usually when just one moves past the other. But in this way, right now Mercury is retrograde, and so it gets closer to Saturn, and then just half a degree before it gets there, then it decides to stop and move away again. So it's interesting to watch, although because the planets are so low at the horizon and it's getting light around that time in the rise, it's not easy to observe. In the evening, we have Uranus still visible at 6 degrees south of the Pleiades. So it's relatively easy to find with binoculars. And Uranus is 6 magnitude. That's just at the limit of naked eye visibility. And there's another planet that it's almost exactly the same brightness. That's the minor planet Vesta, minor planet number 4 in Libra. And it's rising around 8 p.m. So later at night, it's high up. And then next month, it will be closest to us and will get even brighter than 6 magnitude. The moon is tomorrow right next to Mars and Pollux, and so they form a nice triangle. It may be worthwhile to watch it all evening. And then a week later, on the 12th, on the next Saturday, there's the full moon, and at that time it's extremely close to Spica. It's almost so close that you cannot see Spica, but if you look there, you'll see Spica just a little bit above the moon. Thank you.
Thank you so much, Eric. We really appreciate that. Now we have Doug Smith, who is going to present a couple of Astro League awards. So you want this microphone?